In 2022, scientists revealed the first ever image of the supermassive black hole at the center of our galaxy. It's 4 million times the mass of our sun, sitting just 26,000 light-years away. But here's what they didn't tell you. Every galaxy has one, and the connection between these cosmic monsters and the galaxies they live in might be the key to understanding how the universe works. At the heart of the Milky Way, 27,000 light-years from Earth, sits Sagittarius A, a black hole roughly 4 million times our sun's mass. Its gravity anchors entire constellations of stars, yet its event horizon is only about the size of Mercury's orbit, a pinhead in galactic terms. Until recently, astronomers assumed the action ended there. Anything that crosses that boundary disappears forever. Then, a game changer. The Event Horizon Telescope stitched together the first direct picture of its bigger cousin in M87, revealing a bright ring of light against the pitch-black shadow. Suddenly, the monster had a face, and it was beautiful. More importantly, it wasn't quiet. The images showed a lumpy disk, regions clumping up and spilling energy outward, hints that black holes aren't the neat, calm vortices we imagined. They burp, they flare, and, according to papers released this spring, they can even regurgitate matter in ways that seed new stars. The old story about one-way traffic is officially over. Here's the dilemma. James Webb and other scopes have spotted black holes already weighing 1 billion suns when the universe was only 700 million years old. Most models say nothing in the early universe could have grown that big that quickly. It's a truly baffling cosmic conundrum. Two big ideas compete. First, the seed scenario. Stellar mass black holes left by the first colossal stars ate gas at the maximum physically allowed rate for every moment since the Big Bang. The math is tight, but it can be done if you tweak the diet. Second, the heavy seed track. A halo of gas the size of the solar system collapses straight into a black hole of 10,000 or 100,000 suns, jumping way ahead in the game. Both models involve exotic physics, supersonic inflows, weak magnetized turbulence, and possibly an assist from dark matter self-destruction. Whichever way you pick, the timescale problem implies that some black holes may have formed before the stars themselves. That's like finding a mountain in a toddler's sandbox, and it's forcing theorists to rewrite the early chapters of cosmic history. If these mind-benders are the kind of thing you like chewing on, consider hitting that subscribe button and ringing the notification bell. Because we're about to look at the fastest-growing black hole ever recorded. Trust me, you won't want to miss that number. The Wide-Field ASCAP L-band Legacy Survey, Wallaby, recently flagged a galaxy cataloged as WISE J22. It's redshifted so far that its light left only 1.5 billion years after the Big Bang. In its core, a black hole is devouring the equivalent of one sun every 24 hours. Just imagine that. At that mind-boggling pace, it's ballooned to 34 billion solar masses, placing it among the top 5 heaviest ever detected. The disk glows with the brightness of about 10 trillion suns, yet its own radiation pressure doesn't blow the food away. Astronomers call this the Super Eddington regime, where gravity completely wins and photons lose. Jets from the poles punch through the disk, slamming into the intergalactic medium and creating a cocoon of hot gas that will eventually cool into new star-forming filaments. In other words, a single black hole is eating an entire galaxy and simultaneously building a new one. So how do destroyers become creators? It really comes down to scale. When gas is super close to the event horizon, friction can heat it to billions of degrees, hot enough to evaporate surrounding material and effectively stop star birth. But farther out, something different happens. Shock waves from black hole jets can compress clouds just enough to initiate collapse. This dual role of black hole feedback is crucial for galaxy evolution. The Phoenix Cluster's central galaxy illustrates this perfectly. The black hole jet there hits cold gas at a speed of 1,000 kilometers per second, triggering a stellar birth rate of 600 suns per year, hundreds of times higher than our Milky Ways. In other words, the black hole acts like an over-the-top drummer setting the tempo for a galaxy-wide flash mob of star formation. And that's not the only case we've seen. Astronomers now list a dozen galaxies where radio lobes from jet material coincide with freshly minted stars, many only a few million years old. The correlation is simply too strong to ignore. Supermassive black holes, it seems, can act like cosmic espresso shots. They either wake a galaxy up or calm it down, depending on how much you give them. If you're still with me, drop a midwife monster in the comments so we know you're not a bot pretending to like astrophysics. And if you enjoy this channel, do us a favor and share it with someone who still thinks black holes are just cosmic vacuum cleaners. Closer to home, observations from the Chandra X-ray Observatory show Sagittarius A leaking electrons at about 30% the speed of light. These aren't dramatic jets, more like a slow, steady stream of particles tunneling through the galaxy's densest regions. Why should we care about a slow leak? Because that subtle outflow is enough to gently heat the gas around our own supermassive black hole, preventing it from raining down in torrents and igniting the next generation of stars. The Milky Way's star-forming rate is already sluggish compared with galaxies in the early universe, partly because of this gentle thermostat. When you look at night and notice the sky isn't cluttered with brand new blue stars, you can thank a black hole faucet that never turns off. In a sense, our galaxy is on a diet because the drain decided to recycle instead of gorge, illustrating its profound impact on galaxy structure. Next decade, the 30-meter telescope, Euclid Plus, and upgrades to the Event Horizon telescope will let us watch these leaks and fountains in action, not just snapshots. We'll resolve individual clumps of gas being pushed around by black hole winds at resolutions comparable to looking from Earth at a beach ball on the moon. Simulations already hint that dwarf galaxies might host surprisingly heavy black holes relative to their tiny star populations. If true, that would flip the standard narrative that big black holes always live in big galaxies and challenge our co-evolutionary models. We may also uncover the long-sought intermediate mass black holes, the missing link between stellar and supermassive, lurking in the outskirts of our own galaxy. Every one of these discoveries will tighten or break our best formation models. So, supermassive black holes are not what we thought. They're not just cosmic drains, they're cosmic engines. Sometimes blazing furnaces that sterilize a galaxy, sometimes gentle gardeners nudging gas into baby stars. They can balloon from nothing to billions of suns in a cosmic blink, yet they also dribble electrons for billions of years like a leaky sink. They rewrite physics in their origin story, then rewrite biology by deciding whether a galaxy will ever have enough stars to create planets and life. The next time you picture a black hole, don't imagine silence and darkness. Instead, imagine a complex heartbeat at the very core of the galaxy, an invisible drummer that decides how big, how bright, and how alive its host can ever become. And if you want to follow that heartbeat as it echoes through new observations, this channel will be here to translate the wonders.